This animation shows the spread of COVID and its mutations. Each point represents a sequenced COVID genome, and they've been arranged to show the likely mutation pathways. The radius represents the number of significant mutation steps, and the major variants have all been colour-coded. You can see the UK variant up here in the top, a late development but one that spread quickly. This plot shows all the variants of COVID as a tree. It's natural to think of evolution as producing a tree, each variant branching out to several child variants. But we don't actually get to observe the mutations themselves. All we get to see is the resulting diversity. What we really measure in the lab is something like this, a similarity matrix. Think of the x-axis as representing all the genome sequences in our database and the y-axis the same, so that each cell in this matrix represents a pair of genomes. And we'll colour-code the cells by how similar those two genomes are. Biologists have all sorts of ways of measuring similarity between genome sequences based on how DNA mutates. By the way, I've plotted this out as a full n by n matrix, but really we only need to keep half of it because it should be symmetric. The similarity between genomes I and J is the same as the similarity between genomes J and I. So this sort of matrix is what we can actually measure in the lab. How should we go from this sort of data to a nice looking evolutionary tree? That is the topic of this video. Now, this is a series of videos about graph algorithms, so you won't be surprised that our first step is to frame it as a graph problem. Here I've redrawn the similarity matrix as a graph, one vertex per genome, and I've put edges between all pairs of vertices, and I've weighted the edges to reflect how similar the genomes are. Here I'm only plotting edges where the similarity is above a threshold so it doesn't get overwhelming, and I've used an off-the-shelf algorithm to spread out the vertices, trying to keep the high similarity genomes close to each other. By the way, if you're interested in how this sort of layout algorithm works, it falls under the general heading of embeddings in machine learning. I'm going to say a little bit more about embeddings at the end of the course, but I'll skip over it right now because it's not really relevant for graph algorithms. Okay, now we've got this graph, then it's easy to say what we want to produce. How can we find a tree inside this graph? In other words, a subtree, such that our subtree picks up as many high-weight edges as it can. The idea is that if two genomes are very similar, then they're probably very close to each other in the evolutionary tree. As usual, we had better lay out some precise definitions and write down a proper problem statement. I'll leave you to read this, copy it out, and then I'll make some comments. Pause the video and press play again when you're ready. First, let's make sure we have the definition straight. Here is a small undirected graph with edge weights. Pause the video, find a minimum spanning tree, and then press play when you've got one. And here are two different minimum spanning trees that you might have found. First remark, obviously there might not be a unique minimum spanning tree. That's why our problem statement asks for a minimum spanning tree rather than the minimum spanning tree. One other remark, I'm thinking of edge weights as costs, so it's reasonable to look for a minimum weight spanning tree. To solve the COVID evolutionary tree problem, instead of a similarity matrix, I should really be working with a dissimilarity matrix, so that the weight between two genomes is a measure of their dissimilarity, and then I'd look for a minimum weight spanning tree. So, how do we go about finding a minimum spanning tree? Do we have to do some horrible combinatorial search over all possible trees? No, not at all. And in fact, a simple greedy algorithm is good enough. An algorithm which you could probably invent if you gave it 5 minutes of thought. If you're up for a challenge, pause the video now and invent a greedy algorithm for finding a minimum spanning tree. Here's one version of a greedy algorithm. Let's build up our tree edge by edge. If this here in blue is the tree we've built so far, which edge would you pick next? You'd pick the BE edge. That's the obvious choice. It's got the smallest weight among all edges you could pick next. And that's all the algorithm is. It's called Prim's algorithm. Given the tree that we've built so far, we look at all the vertices that we might add next, call it the frontier of vertices, and we pick the lowest weight edge across the cut between our tree and the frontier, and repeat until we have a spanning tree. There's an assert statement I stuck in here. This assertion is something that will come into the proof of correctness. The proof is just another breakpoint proof. We assume that the assertion is true up to iteration n-1, and then we use maths to argue that it will be true after iteration n, and then, by induction, it's true all the way until the algorithm terminates. The maths of the induction step is a bit more fiddly than I want to go into here. It's just plain discrete maths and it's quite accessible, and if you're interested you can find it in the accompanying lecture notes. And the details of that proof, by the way, unlike most of the other proofs in this course, that proof is not examinable. Now, let's turn this into code. It'd be pretty daft to implement it directly as I've stated here. We don't need to recompute the frontier on every iteration. All we have to do is update it based on the edge we just added. What you should try and do now, without looking at the code, is to come up with the pseudocode yourself. How would you update the frontier? Pause the video, have a go, and then come back and we'll look at Prim's answer. Here is what Prim's algorithm does. It uses a priority queue to store the frontier. You should be having flashbacks to Dijkstra's algorithm right now. The only difference between this and Dijkstra's algorithm is that there's slightly different logic for setting the keys for vertices. We want the key to measure the distance from each vertex to the tree that we're building up. So, when we pop a vertex from the frontier, and we're looking at its neighbour w, we'd set w.distance to be equal to the weight of the VW edge, unless w is already closer to the tree via some other edge, and of course if w is already in the tree then we won't consider it at all. As I said, this is pretty much the same algorithm as Dijkstra's shortest path algorithm, just with a small difference in how we measure distances, and so it's no surprise that exactly the same complexity analysis carries through. Prim's algorithm is also big O of E plus B log V. Okay, so that's Prim's algorithm for finding a minimum spanning tree. But when I challenged you to invent your own greedy algorithm for finding a minimum spanning tree, there are probably a few of you, the right-brainers, who went in a different direction. You might have come up with a completely different greedy algorithm, one that goes like this. Let's build up our tree out of a forest. We have lots of little trees, and we'll join them together step by step. If you saw this forest, which edge would you add next to join two trees? Pause the video and have a think. This is a trick question. Left-brainers, like me, look at this graph and see two trees. Right-brainers look at it and they see four trees. The two obvious trees plus two single vertex trees. Now it's much easier to understand what needs doing. We just pick the lowest weight edge that will join two of these four trees, in this case the GH edge, and we just do this repeatedly. This is called Kruskal's algorithm, and here are all the steps written out. Press pause and have a read. You'll see that the proof of correctness is pretty much the same as for Prim's algorithm, and in the lecture notes I actually set them out to share a common lemma. When we try to take this algorithm and turn it into code, it's natural to look for optimizations. And this is what comes to mind. Is there a way that we can avoid having to recompute the set of candidate edges on every iteration? This is what Kruskal's algorithm does. It pre-sorts all the edges, lowest weight edge first, and then it just goes through the list, and any edge it comes across that joins two vertices that are already in the same tree, it just ignores those edges. Now, in this code, there is a novel data structure called the disjoint set. We need to keep track of which vertices belong to which trees, and that's the sort of task that disjoint set is designed for. It lets us query to get the set containing a vertex. It lets us merge two sets together, and for the initialization part of an algorithm, we also need to create new sets consisting of a single item. We're going to be looking more carefully at this data structure in the next part of the course, and we'll study how to implement it efficiently. But for now, all I'm going to say is what the complexity is. Each of these three operations is a big O of 1-ish. Ish isn't part of the big O notation that you've learnt about yet. It's what we're going to learn about in the next part of the course. Anyway, now we can easily work out the running time of Kruskal's algorithm. The biggest cost is sorting the edges, which is big O of E log E. And when we add everything together, we get big O of V plus E log E. But it's more usual to simplify this expression as follows. I'm going to leave you to read this. There isn't anything exciting to say about this, it's just some basic algebra. Pause, read through this, and once you're ready, hit play. Okay, so we've learnt about minimum spanning trees and how to find them. I want to finish this video with a little digression which is very close to my heart. I'm a data scientist, and what I really love about algorithms is when they give me some new insight into my data. So here's a cunning way to use Kruskal's algorithm to help me understand a data set. I'll show you the idea first on a toy graph and then we'll apply it. Here is a simple graph. And let's run through the steps of Kruskal's algorithm. First, we pick out a minimum weight edge in the entire graph. In this case, the EF edge. I'm going to draw our edge on the right, as shown here. Next, we join A and B, and again, I'll draw out this edge that we've chosen. The next edge we pick is from E to C, but I'm going to draw it differently. I'm drawing it to emphasize that what we're joining is we're joining C to the cluster made up of E and F. Likewise, the next edge we pick joins D to the cluster formed from A and B. And so, at the end of it, what we've produced can be thought of as a classification tree. The difference between this classification tree and the spanning tree on the left is that our classification tree has some extra branch nodes and it puts all the vertices as leaves. Anyway, what can we do with the classification tree? Well, remember the genome similarity matrix we saw at the beginning of the video? I lied. It's not a genome similarity matrix. It's a matrix that measures the similarity of submitted coursework. Any Cambridge students who are watching this video, when you upload your coursework to Moodle, it computes a similarity score between your work and that of all the other students. And the similarity matrix here is for tick 1 for Lent term 2021. Okay, so I took this similarity matrix and I get myself a nice classification tree. And now I'm just replotting the similarity matrix, but I've reordered the students according to where they fall in the classification tree. This makes it much easier to see the clusters. There are two big blobs. One is for students who chose to submit their work in Java, the other for students who chose to use Python. There's no similarity at all between Java code and Python code. And inside the big blobs, I can see smaller clusters of students who might have been helping each other out. Anyway, I hope you enjoyed this little detour into data science.